The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
So the first presenter is Gian Piatos. He's a graduate student from the University of California at Los Angeles, in Los Angeles, California, and he's going to talk about design and modeling issues related to diaphragms of tall buildings.
Hello, I'm Gian Piatos from University of California, Los Angeles, and my advisors for this project were John Wallace of UCLA and Kristijan Kolozvari of Cal State Fullerton. So the focus of this study was looking into modeling of tall building diaphragms for performance-based seismic design. So talking with my advisors, we found some variances in the design and modeling of diaphragms across multiple different projects. And so what we want to take a look into is to kind of do a sensitivity studies into different modeling configurations and different modeling parameters for the analysis of diaphragms. Mainly we're going to be focusing on transfer level diaphragms and also looking a little bit into the tower level diaphragms. So one of the objectives is to look into the sensitivity of the demands when you model a transfer level diaphragm as linear elastic versus modeling it as a nonlinear diaphragm. And also another objective is to compare forces obtained from a finite element analysis to a more simplified methods such as analyzing the diaphragms as a rigid beam with rigid supports. So the software we used for this study was Perform 3D as standard, something normally used in regular practice. So the building used for the study is a 38-story residential building with a 7-story podium, and the main lateral force resisting system is a concrete core wall. And then starting at the 6th story, there are some more shear walls that are introduced, and then finally at the basement levels there are some basement walls. So this building is a recently completed design, and it was designed according to the guidelines of the LA Tall Building Seismic Design Council guidelines. So for the Perform 3D model, the RC core was modeled using a nonlinear shear wall. Podium walls were also nonlinear shear walls, and basement walls were elastic shell, while the diaphragm for the transfer level was elastic shell. But for the transfer level, in order to do the nonlinear modeling and the comparison between the linear elastic, we used the elastic shell, which was originally used, and then we used the nonlinear general wall to model the nonlinear behavior. And also, additionally for this, when we're looking at the tower level to do the comparison between this, using a beam analogy, we used the elastic shell to model the tower level as well. So this slide shows the mesh that was used for both the transfer level and the tower level, as well as the location of the masses. So we used a much finer mesh than it was in the original model in order to better accurately capture the forces in the diaphragm, and also to, when we do force envelopes, which is how we compared the beam analogy, to get a much more accurate shear and moment envelope as well. And then over here is just going through an explanation of the different elements types we use to model the transfer level. So the linear elastic shell, it's a linear elastic element. It's typically used to model the diaphragms. And in-plane behavior is modeled as a membrane, while out-of-plane behavior is based on elastic beam. And then for the nonlinear behavior, is used the general wall element, which it's typically used to model shear walls, but in this case we use it to model the diaphragm because it's able to capture axial and flexural behavior in both directions, as well as shear behavior. And the way it's done is through uniaxial backbone curves for concrete, steel, and then the shear behavior. So you can see right below in those figures, the leftmost figure is just an image of the elastic shell element, and then the figures to the right are the general wall element components, being vertical axial bending, horizontal axial bending, and then the concrete shear behavior. Additionally, there's one more component in the general wall element which we didn't really use, which was it's able to also capture the behavior for diagonal shear, which would be the compressive strut. But because the modeling of the parameters for that backbone is not really known, we decided to skip that because it's really optional. The main portions really are just the concrete steel and then the shear behavior. So the diaphragm demands we decided to look into to do these sensitivity studies are just typical demands. So drag force, slab shear, and then the chord force. And we looked into how sensitive these results are for modeling as linear elastic, nonlinear, and also different effective shear stiffness parameters. So this is the results we had for the slab shear. We mainly focused on the demands around the core wall. And then the figure on the right shows the average plus or minus the standard deviation for a set of 7 ground motions. So you can see that the triangles represent the results for the nonlinear diaphragm, and you can see that it's slightly higher than modeling it as a linear elastic. And another thing to note is the trends with different effective shear stiffness values. So the shear stiffness values we use for the slab are 0.15, 0.25, and 0.50 of the gross effective shear stiffness. And you can kind of see for the linear elastic, there's not really an actual trend to it. So you can see on one of them, it's increasing as you increase the effective shear stiffness, but for another, it's decreasing. But when you look into the nonlinear diaphragm, it's consistently increasing for the most part, but at different magnitudes. And then next up is the drag force. And then we took a look at both the compression drag as well as tension drag, but just for one side of each wall pier. So for these demands, the elastic shell usually reported higher forces for the compression drag, while for the tension drag, the nonlinear diaphragm reported higher forces. And this is mainly for these sides of the walls where there's a lot of transfer between these walls in the diaphragm. But in these areas of the diaphragm where there's not really any force transfer, the results between the linear elastic shell and the general wall are much closer to each other, but there's barely any difference, especially in the tension drag. There's a slight difference in the compression drag, but not very much though. And then the last one would be the chord force. So for this one, we took section cuts over here, which would, if you think of it as a beam, it would be right approximately mid-span. And so we looked at the differences between when you take the maximum positive, maximum negative moment, and the results are very, very different when you look at either one. So for maximum positive is shown right here on the left, and then maximum negative is shown here. So you can see on this one, this is section cut 1. This is showing that the nonlinear general wall is reporting much higher chord forces than the elastic shell, but then when you look at the negative, they're much, much closer to each other to where they're about the same. But then on the second section cut right here, the forces are almost the same between the different elements, but then on here, the nonlinear elastic is reporting much higher forces for some reason. Next over here is we're comparing the results from a finite element analysis to estimating demands using a simplified method such as a beam analogy. So this is how we estimated the forces. So here is the tower level of the diaphragm. One of the tower levels for the building, and this is how we idealize it to simplify the calculation. So we assumed it as a rigid beam with rigid supports and uniformly distributed loading. However, we considered two different kinds of loads. We considered the regular translational acceleration, and we also decided to look into what happens if we take into consideration the twisting that the levels experience. So the way we did that is this partial bow tie loading, which would equate to the inertial moment that that level would experience. So, and then lastly, for the translational response, we took not only the responses we used were the acceleration responses that were reported from Perform 3D, but also using the FPX forces calculated from using the ASCE7 equivalent lateral force method. So the following diagrams, this is only when you take into consideration the translational response. So just as translational acceleration from Perform 3D and the FPX forces from ASCE7. So over here, this is the direction of the earthquake we just looked into. We just looked at one direction. And then so the blue represents the acceleration response that we got from Perform 3D. So this was taken as the mass times acceleration of the floor. And then the orange was the ASCE7 equivalent lateral force. So you can see that it not only does it underestimate the forces that you could get from Perform 3D, which is the black. This is the envelope made from getting section cuts on the diaphragm, but also it's unable to capture the shape properly. As you can see over here, it's not, where using the hand calculation, we get points of zero moment. We actually get some amount of shear at these locations. And also over here is the bending moment, and you can see it also underestimates the forces from Perform 3D. And then over here is the transfer level, and then this is the direction of the earthquake. So over here is the shear force. So unlike the tower level, the shear force is actually overestimating the Perform 3D forces for the shear, but then underestimating it for the bending moment. But then the reason maybe for this is because of how the diaphragm is, in that it's much stiffer due to the additional walls, as well as it being a lower level. But for some reason the bending is being underestimated, maybe due to the reason that there's much more, the diaphragm is much more flexible than what we thought with the simplified method. But then with the simplified method, we assumed a rigid beam, so it didn't really take into account the fact that the transfer level is much more of a semi-rigid rather than a rigid beam. And then last couple of diagrams is if we take into consideration the effect of if we take into account the twisting that each of the floors experience. So when we take into account into the twisting for the tower level, it's able to better match the forces from Perform 3D. So with a slight overestimation, and then when we do that, where there's no more points of zero shear anymore, and it's more of this parabolic shape. But then in the bending moment, there are points where there's zero moment, even though in Perform 3D there's still no zero moment. And then over here is the transfer level. If you can tell, the diagrams have barely changed from when you take into account just the translational, and this is because this level, it's the sixth level of the tower, and so it's not really experiencing as much twisting as the tower level, and then not only that, but this level is also much stiffer, so it's not experiencing as much twisting. So the rotational acceleration is not really having as big of an effect on this level. So in summary, from this small study we did is, right now what we're getting from Perform 3D and the results we're getting is there's not really much of a trend going on with modeling the diaphragm as nonlinear versus linear, as well as there's no real trend really right now with the effective shear stiffness values that we're getting. Because as you kind of saw there from the slab shear, there was locations where a higher effective shear stiffness on the slab would result in a higher slab shear, but in other locations a higher shear stiffness would result in a lower slab shear. And then from the drag force, you kind of saw for modeling between nonlinear and linear, the compression drag tends to get higher when you model the diaphragm as linear, but then tension drag is higher when you model it as nonlinear. And then for the beam analogy, when you try to estimate the diaphragm forces with assuming it as a rigid beam, the beam analogy is better estimated when you try to include torsion into it rather than if you just try to use translational forces into it. And then for the transfer level, that one, whether you include rotational acceleration into it or not, it doesn't really affect it as much because it's a much stiffer level. But even then, with the assumptions we made with doing the hand calculations, it doesn't really take into account that the fact that transfer level is